Caterpillar broke every rule of diesel engine design. While their competitors built engines to meet warranty periods and fuel economy targets, Caterpillar took what they'd learned from decades of powering earth-moving machines and applied it to the highway, assuming engines would be abused, rebuilt, and abused again. The result was something drivers would call unkillable, changing trucking forever. Caterpillar's engineering rulebook came from yellow iron, not the highway. Bulldozers ran at full load for entire shifts. Mining trucks clawed through dust and heat with no margin for failure. Generator sets couldn't limp mode during a blackout. That environment forced CAT to build engines with massive safety margins. Thick main webs, oversized bearing surfaces, deep induction-hardened crankshafts, and blocks designed to resist distortion under constant stress. When Caterpillar decided to enter the highway market, they didn't abandon these principles. They applied construction equipment engineering to over-the-road applications, creating engines that treated highway operation as light-duty compared to their intended design parameters. The 1693, introduced around 1970, brought construction DNA to highway chassis. This 14.6-liter engine featured the heavy cast iron block construction that Caterpillar had perfected in off-highway applications. The block casting included thick webbing between main bearing caps, creating a rigid foundation that resisted bore distortion under load. Large journal diameters distributed crankshaft loads across maximum bearing surface area, reducing unit pressure on wear surfaces. Unlike many industrial engines of the era, the 1693 utilized a single overhead camshaft design. While most construction engines relied on cam-in-block pushrod layouts, the overhead cam allowed improved breathing and more stable high RPM operation for sustained highway use. It wasn't just a construction engine shoved into a truck, it was a serious highway power plant. While most heavy-duty competitors also used forged steel crankshafts, Caterpillar distinguished itself through massive journal dimensions and deep induction hardening, increasing fatigue resistance under sustained high load. The crankshaft featured large counterweights that balanced rotating forces and reduced vibration transmission to the block structure. Like its heavy equipment siblings, the 1693 used fully gear-driven timing and accessory drives, standard practice among heavy-duty diesels but critical to long-term timing stability. The gear train drove the injection pump, oil pump, and cooling system directly from the crankshaft, ensuring precise timing throughout the engine's service life. Mechanical injection systems provided fuel delivery without electronic sensors or complex control modules that could fail in harsh operating conditions. The 1693 used a direct injection combustion system that optimized fuel burn and heat distribution under sustained load. This approach affected thermal patterns on pistons and cylinder heads while maintaining efficient fuel consumption. The controlled combustion also influenced stress patterns on connecting rods and main bearings, contributing to extended component life. The 1693 was typically governed around 20/100 RPM and was comfortable operating in higher RPM ranges than many later engines. Its torque characteristics supported strong highway pulling power, but the major shift towards sustained low RPM cruising and economy operation emerged with later 3406 variants and the calibration strategies of the 1980s. The mechanical advantages of this approach became apparent in stress cycle mathematics. Fatigue failures in engine components result from repeated loading and unloading cycles. Each crankshaft revolution subjects bearings, connecting rods, and pistons to complete stress cycles. Higher RPM operation multiplies these cycles proportionally, accelerating fatigue accumulation in critical components. Consider two engines covering identical mileage over their service lives. Engine A cruises at 2100 RPM, typical for highway diesels of the era. Engine B, representing the Caterpillar approach, cruises at 1400 RPM. At 2100 versus 1400 RPM, the higher revving engine racks up about half again as many crankshaft revolutions over the same distance. This difference translates directly into bearing fatigue life, connecting rod stretch, valve train wear, and oil shear rates. Mean piston speed increases directly with RPM, creating higher inertial loads on connecting rods and main bearings. Valve train components cycle more frequently, accelerating wear on camshaft lobes, lifters, and valve guides. Oil molecules experience higher shear rates at elevated RPM, breaking down lubricant films and reducing protection of critical wear surfaces. The 1693 proved that construction equipment architecture could succeed in highway applications, but it also revealed opportunities for refinement. The engine's weight and size limited its applications, and certain design elements could be optimized for over-the-road service. Caterpillar used this experience to develop the 3406, an engine that perfected the integration of heavy-duty engineering principles with highway packaging requirements. The 3406, introduced in the mid-70s, was designed as a more compact alternative to the larger 1693, allowing Caterpillar to fit a wider range of highway chassis while carrying forward its durability philosophy. Unlike the 1693's overhead cam layout, the 3406 returned to a cam and block pushrod design, reducing overall engine height and improving packaging flexibility without sacrificing structural strength. At the time, many highway engines were chasing horsepower numbers and lighter packaging. Thin main webs reduced weight, narrower bearings reduced friction. Blocks were cast closer to minimum tolerance to save material cost. On paper, the math worked. On the road, under sustained heavy haul, those margins disappeared. Capwalk developed, bearing edges loaded unevenly. Thermal distortion crept into cylinder bores. None of it catastrophic at first, just incremental fatigue accumulating mile after mile. Caterpillar's answer wasn't higher RPM or lighter castings. It was more iron. Wet replaceable cylinder liners formed the foundation of the 3406's rebuildability. Unlike dry sleeve designs that required machining the block when cylinders wore beyond tolerance, wet liners could be pulled from the top of the engine and replaced with new components. This approach preserved the expensive block casting through multiple overhaul cycles, reducing the total cost of ownership and encouraging rebuilds rather than engine replacement. The 7-main bearing design provided rigid crank support across the engine's long-stroke architecture. Additional main bearings reduced the unsupported span between bearing caps, minimizing crankshaft deflection under load. This design prevented the bearing edge loading that caused premature failures in engines with inadequate crank support. The one-piece cast iron cylinder head incorporated replaceable valve seats and guides, allowing refurbishment without scrapping the casting. Instead of replacing an entire head when wear occurred, technicians could service individual components, reducing cost and preserving the engine's core structure. The in-frame overhaul design represented perhaps the most significant advancement in highway diesel serviceability. Traditional engine rebuilds required removing the engine from the chassis, transporting it to a machine shop, and performing extensive disassembly. The 3406's architecture enabled complete rebuilds with the engine remaining in the frame, dramatically reducing downtime and repair costs. Bearing life comes down to surface area and load. Caterpillar attacked both. Larger journal diameters spread force across more material. Wider bearings reduced unit pressure. Rigid blocks kept everything aligned under load. The result was simple. Oil film survived longer, metal touched metal less often, and fatigue took dramatically longer to accumulate. This is why heavy haul operators gravitated toward the 3406. Gross weights climbed, mountain grades got longer, drivers lugged engines down instead of screaming them at redline. Where lighter engines began to show bearing wear or head gasket fatigue, the 3406 just kept pulling. Fleets learned something simple. If you rebuilt a 3406 on schedule, the block and crank were almost never the failure point. The expensive parts survived. The in-frame overhaul process demonstrated this approach in practice. Technicians could drop the oil pan, roll in new main bearings, and pull cylinder liners from the top of the engine without removing the block from the chassis. Piston assemblies could be replaced, injector heights reset, and the engine reassembled to factory specifications in a fraction of the time required for traditional rebuilds. Most importantly, the in-frame overhaul capability meant that wear did not equal death in Caterpillar engines. Components could be restored before reaching failure points, preventing the cascade failures that destroyed engines designed with less robust architectures. Real-world consequences validated Caterpillar's engineering approach. owner-operators consistently reported 500,000-mile intervals between major overhauls, with many engines exceeding 1 million miles before requiring significant repairs. Multiple in-frame rebuilds became common practice, with some engines accumulating well beyond 1 million miles across multiple rebuild cycles before reaching end of life. Fleet managers specified Caterpillar engines despite higher upfront costs because total cost of ownership calculations favored the rebuildable architecture. Used 3406 engines commanded premium prices in secondary markets, with buyers specifically seeking cores for rebuild programs. The glider truck industry, which installed rebuilt engines in new chassis, relied heavily on Caterpillar power plants because of their proven rebuildability. Heavy haul operators who subjected engines to sustained high load operation overwhelmingly preferred Caterpillar engines. These applications most closely resembled the construction equipment duty cycles that had shaped Caterpillar's engineering philosophy, and the engines performed exactly as designed under these demanding conditions. Those results weren't luck, they were engineered. Wet liners prevented cylinder wear from scrapping blocks. Multiple main bearings distributed crankshaft loads. Forged crankshafts resisted fatigue fractures. Replaceable valve seats prevented head scrap. In-frame overhaul capability encouraged multiple rebuild cycles. Every design element contributed to preventing terminal failures. The reason multiple rebuilds were even possible came down to structural integrity. In many engines, repeated heat cycles and high cylinder pressures eventually distort the main bearing saddles or shift the block deck out of flat. Once that happens, a line boring becomes necessary, and eventually the block is scrap. The 3406's thick main webs and deep skirt block architecture resisted that distortion. Main caps stayed seated. Crank centerline remained true. The block didn't walk over time. Wet liners also isolated cylinder wear from the parent casting. Combustion pressure and heat stayed contained within a replaceable sleeve rather than eroding the block itself. Rebuild after rebuild, the expensive iron structure stayed dimensionally stable. That's what separated a rebuildable engine from one that was merely repairable. The 3406E arrived in the early 1990s and replaced the traditional mechanical injection pump with electronically controlled unit injectors. Each injector was mechanically actuated by the camshaft, but timing and fuel quantity were controlled entirely by the ECM. The 3406E would later evolve into the C15, the final and most powerful iteration of Caterpillar's highway engine architecture. It retained the deep skirt block, wet liners, and massive crankshaft structure while incorporating ACERT emissions technology and higher injection pressures. For many operators, the C15 became the last true expression of Caterpillar's overbuilt highway philosophy. While the camshaft still supplied the mechanical force required for injection, engine operation was now dependent on electronic inputs. A failed sensor or ECM issue could prevent the engine from running, marking a clear departure from purely mechanical systems. This was the first time Caterpillar's highway engine could be disabled by a wire instead of a broken rod. For some operators, that felt like vulnerability. But underneath the harnesses and sensors, the iron hadn't changed. The block was still massive, the crank still overbuilt, the liners still replaceable. However, these electronic failures rarely caused terminal engine damage. The robust block, crankshaft, and bearing structure continued to provide the durability that had made Caterpillar engines legendary. Electronic controls could be repaired or replaced without affecting the engine's fundamental integrity. The gear-driven architecture proved particularly valuable as electronic complexity increased. While other manufacturers relied on timing chains or belts that could stretch or break, disrupting precise injection timing, Caterpillar's gear train maintained timing integrity regardless of electronic system status. This precision became more critical as injection timing windows narrowed to meet emissions requirements. The heavy cast iron construction provided thermal mass and structural rigidity that helped resist distortion under high heat loads. The thick webbing between cylinders created heat transfer paths that prevented localized hotspots from developing into catastrophic failures. The wet liner system also provided targeted cooling at the top of the liner, where combustion heat is most intense, helping control thermal distortion in the most highly stressed area of the cylinder. Bearing technology evolution demonstrated Caterpillar's commitment to continuous improvement within proven architectures. While maintaining the large journal diameters and multiple bearing configuration, Caterpillar incorporated advanced bearing materials and surface treatments that extended service intervals. Tri-metal bearings with improved fatigue resistance and better conformability reduced the risk of bearing failures even under extreme loading conditions. The connecting rod design reflected similar evolutionary improvements. Forged steel construction provided the strength necessary for high torque applications, while precision machining ensured consistent bearing clearances and optimal load distribution. The rod-to-stroke ratio optimization reduced side loading on cylinder walls, minimizing liner wear and extending service intervals. This approach proved crucial as injection pressures increased to meet emissions requirements. Higher pressures created greater stress on injection system components, but Caterpillar's robust design provided the strength necessary to handle these increased loads. The electronic unit injection system combined electronic control with mechanical durability. Valve train durability reflected the heavy-duty design philosophy applied to highway service. Larger valve stems and guides distributed loads across greater surface areas, reducing unit pressures that caused premature wear. The gear-driven camshaft eliminated timing chain stretch that affected valve timing in competing designs, maintaining precise valve events throughout extended service intervals. Oil system design reflected the continuous duty philosophy that shaped all Caterpillar engine systems. Larger oil pumps and increased oil capacity provided superior lubrication under sustained high-load operation. Full-flow filtration with bypass capability ensured continuous oil circulation even if filters became restricted, preventing the oil starvation that caused bearing failures in less robust designs. The oil cooling system integrated with thermal management strategy to maintain optimal oil temperatures under varying load conditions. Larger oil coolers prevented oil degradation that accelerated bearing wear and reduced service intervals. This attention to oil system design reflected Caterpillar's understanding that lubrication system failures often triggered cascade failures that destroyed otherwise durable engines. Turbocharging integration demonstrated how Caterpillar adapted new technologies to their proven principles. Rather than designing lightweight, high-speed turbochargers that maximize power density, Caterpillar specified robust turbochargers that could withstand sustained high-load operation. Heavy-duty mounting brackets and vibration isolation prevented the fatigue failures that plagued turbochargers in less robust installations. But the world was changing around Caterpillar's iron philosophy. Emissions regulations tightened throughout the 1990s and 2000s, demanding sophisticated after-treatment systems and precise electronic controls. Fuel economy became paramount as diesel prices climbed. Weight restrictions pushed manufacturers toward aluminum and thin-wall castings. The very attributes that made Caterpillar engines unkillable became liabilities in a market obsessed with efficiency. Emissions compliance demanded cooled EGR, complex turbo compounding strategies, and eventually after-treatment systems that required tight integration between engine and chassis manufacturers. That meant higher combustion temperatures, more soot loading, and greater thermal stress inside engines that had originally been designed around mechanical simplicity. Meeting those standards without sacrificing durability required massive R&D investment into systems that didn't necessarily improve engine longevity, only compliance. And compliance margins were shrinking faster than rebuild intervals. Caterpillar faced a choice: redesign the platform around emissions-first architecture or double down on the heavy, serviceable design that had defined them. Redesigning meant sacrificing the rebuildable simplicity that made the 3406 legendary. Not redesigning meant falling behind regulatory requirements. For a company built around construction equipment, margins, and lifecycle durability, the economics of highway emission certification grew harder to justify every year. In 2008, facing the upcoming EPA emissions deadline that would require a complete architectural redesign, Caterpillar announced it would exit the U.S. on-highway engine market. Rather than re-engineer the platform around emissions-first design, Caterpillar chose to stop certifying its heavy-duty highway engines. The company briefly partnered with Navistar to produce Cat-branded vocational trucks, but the era of new yellow engines in highway tractors was over. Ultimately, Caterpillar's highway engines didn't fail, the market simply moved on.